The binomial theorem and inversion of the zeta and eta function show that the odd zeta and eta function and the subordinate zeta and eta function can all be obtained with the zeta function. Since the eta function converges in the critical strip, the zeta function in all regions can be obtained by analytic continuation. In addition, the zeta function can be obtained by the expansion of the negative even zeta function by the inversion of the zeta function. The blue zeta function is a negative even zeta function with 60 terms, and it shows an error of more than 12 decimal places with the red GeoGebra mathematical function. The correction term of the zeta function for negative integers is proven in the coefficients of the zeta function and eta function, and the binomial theorem of the zeta function is established in the negative domain by the pole of the zeta function. In the continuous region other than negative integers, the binomial theorem of the zeta function by the correction term of the zeta function is established, and the purple zeta function is the binomial theorem of the zeta function with 10 terms added to minus s, showing an error of more than 5 decimal places. Although it is a very large error compared to the inversion of the blue zeta function, it means that the binomial theorem of the zeta function is established not only in the positive direction, where it converges, but also in the negative direction, where it diverges, since it is a value obtained only with the zeta function of negative integers. If the generalization of Faulhaber's formula is applied, the error of the binomial theorem of the purple zeta function can be reduced. The generalization of Faulhaber's formula is that if the number of terms is increased in the region where s is greater than -1 and less than 1, it becomes very close to the zeta function. However, if the number of terms is increased in the region where s is less than -1, the error becomes very large. Therefore, the generalization of Faulhaber's formula in Brown can reduce the error to more than 8 decimal places by applying 20 terms of the Bernoulli number to the sum of only 2 terms in the region where s is less than -1. In the region where s is greater than -1 and less than 1, 20 terms of the Bernoulli number are applied to the sum up to 50,000, and the error is more than 10 decimal places. If the binomial theorem of the zeta function holds in the negative direction, the binomial theorems of the zeta function and eta function hold in general without the need for proof. In addition, a more accurate zeta function can be obtained with much smaller terms than the eta function that converges in the critical strip, and it is proven that the zeta function for rational numbers is an algebraic number in the region where s is less than 1.